Welcome once again back to Physics with Ben. This is the continuation of the video series on electric field 1. In the first video, we talked about electric field, Coulomb's law, electric field intensity, and electric potential. And then in the second video, we talked about capacitors and capacitance. We looked at what a capacitor is. We said that a capacitor is simply an electrical device that stores electric charges. We said that the capacitance for a capacitor, the capacitance of a capacitor is simply the measure for the ability of a capacitor to store electric charges. And then we also looked at the symbol for the capacitor as something like this, a plus and then a negative. Look at something like this. We also look at the circuit concerning a capacitor. Kindly watch video 2 on this series. We also look at arrangements of capacitors in series and in parallel. We said something that was very, very important, which I would love to re-emphasize for the sake of emphasis. We said that when capacitors are arranged in series, you add them as if you are adding resistors in parallel. And then when capacitors are in series, just as resistors in series, when resistors are in series, you have the same electric currents flowing through them, but different potential difference across each of the capacitor. Similarly, when capacitors are in series, you have the same electric currents flowing through each of them, the same quantity of electric charge flowing through each of them, but however, you have different potential difference across all of them. The only thing that you have there in difference is that you add capacitors in series as though you are adding resistors in parallel. We look at capacitors in parallel. That when capacitors are in parallel, you add to find the combined capacitance as if you are looking for the combined resistors when they are in series. And then there's something common. When capacitors are in parallel, they have the same voltage, but then different electric currents and different quantity of electric charge. Just that when you have resistors in parallel, what you have? You have the same voltage, different currents, and that is it. So we also looked at the parallel plate capacitor, where I drew something like this. I still want to emphasize this diagram because in the other video I rushed over it and I did not explain it properly. So this is plus, this is plus, this is negative, negative, plus, negative. Current will flow this way, back, and then to this way again. So in between here is what we call the dielectric material. The dielectric material is simply the material that is placed in between the parallel plate capacitor. The material behaves as though it is like a conductor, an insulator. So this is what we call the dielectric material. It behaves like what? It behaves like an insulator, an insulating material. Then we said that in between these plates of the capacitor, there's what we call these guys, they have a distance of separation between them called D. The distance of separation between them. That again, that when these guys, when they are connected to a power source, to an EMF source, an electric field E is generated in this direction. An electric field E is generated in this direction. And again, that in between this space, we assume that there is a free space, and then we call it the permittivity of free space. The materials also have a permittivity to allow current to flow through them, so we call it permittivity of the material. And so we say that this is absolute R. The plates also have area. That is how wide the plates are. Are they wide like this? Yes. So we call it the area of the plate. So I'm trying to write some small A's here to represent area of the plate. Area of the plate. So that is that for that. So combining all of this, we can now say that the capacitance of a parallel plate capacitor has a direct relationship with the areas of the plate and an inverse relationship with the distance. It also has a direct relationship with the permittivity of free space and the permittivity of the material. So we can say mathematically that the C varies directly with A and inversely with D. Then a moment the examiners may ask you that you should list the factors that affect the capacitance of a parallel plate capacitor. What will you tell them? Simple. The factors affecting the capacitance of a parallel plate capacitor are just few. Number one, we have the area of the plates. We have the distance of separation between the plates. Now, we also have permittivity of the material and also permittivity of free space. If we want to get rid of this symbol of proportionality, we can say that our C is given as absolute naught, absolute R, A, all over D. I repeat again. Increase in the permittivity of free space or the permittivity of the material will cause a corresponding increase in the capacitance of the parallel plate capacitor. Increase in the area of the plates, that is to make the plates to be very wide, maybe as wide as something like this. Then you're going to have great capacitance in the circuit. Now, when you also decrease the distance, you make the distance to be so small, you are going to have very high capacitance. So, in summary, the factors affecting the capacitance of a parallel plate capacitor are simply area of the plates, permittivity of free space, permittivity of the material, and distance between the plates. How do they affect? The area of the plates varies directly with the capacitance of what? The capacitor. In this case, the area is an independent variable, while C is dependent. The D is also an independent variable, while C is dependent. That is, C depends on the value of D. C also depends on the value of A. C also depends on the nature of the material. C also depends on the permittivity of free space. So in this, C is the only dependent variable, while all of these are independent variables. So in today's video, we want to look at the energy stored in a capacitor. Go back and watch the other videos and you get more understanding of what I just explained. The energy stored in a capacitor is given mathematically as W is equal to what? V times Q. Call this equation star, where V is the potential difference in the capacitor. However, during the charging of a capacitor, there's what we call the average value of the potential difference. So the capacitor is charged this way: 0 to peak, it will discharge. 0 to peak, it will discharge. So it is like this. That is how it is charged. So we can write that the average value of the voltage in the capacitor is given as what? 0 plus V divided by 2. It begins from 0, it charges to full, and then back to this. So we can say that the average value of the voltage is given as V all over 2. We can call this equation star star. And so we can write again that the work done in charging a capacitor is given as W equals to what? V average. W equals to what? V average times Q. So substituting equation star star into equation star, we are going to have something like this. That W is given as what? V all over 2 times Q. So we can say that W is equal to what? QV all over 2. You can call this equation number 1. Now, we are still going to generate more equations to have other complex values of the work done. That is advanced equation. Using what I call the physics of cut and join and substitution. What do I mean? Recall that C is equal to what? Q all over V. The general equation for the capacitance of a capacitor. Call this equation star star star. We are free to write again that. You know, from here we have W is equal to QV all over 2. So we are going to make Q the subject formula here and also make V the subject formula. So let's write. So we have C is equal to what? Q all over V. So our Q is equal to what? CV. Call this equation A. Still from here, we want to make V the subject of the formula. So we say that our V is equal to what? Q all over C. We call it equation B. We are going to substitute equation A into equation 1. So write that W is equal to what? Q is given as CV, right? So say CV times V divided by 2. So if we do that, we're going to have W is equal to what? CV squared all over 2. You can call this equation number 2. We are still going to substitute equation B into equation 1. If we do that, we're going to have W is equal to what? Q times Q all over 2 divided by 2. Sorry. We have what? We are substituting equation B into equation 1. So we have W is equal to what? Q times V. V is Q over C. Q all over C divided by what? 2. So if you evaluate correctly, you have W is equal to what? Q times Q. You have Q squared all over 2. All over C. All over 2. So this means that Q squared all over C times 1 all over 2. So we have W is equal to what? Q squared divided by what? 2C. You can call this your equation number 3. So in summary, the work done in charging a capacitor is given as W is equal to V average times Q. W is equal to what? W is equal to what? V is QV. QV all over 2. W is equal to what? Is equal to W is equal to C V squared all over 2. And the last one is W is equal to what? Q squared over 2C. So we call this equation 1, equation 2, equation 3. So in physics, we are free to say that W is equals to QV all over 2 is equals to CV squared all over 2 is equals to what? Q squared over 2C. So it implies that QV all over 2 is equals to what? CV squared all over 2. It also means that QV all over 2 is equals to what? Q squared all over what? 2C. And then it also means that CV squared all over 2 is equals to what? Q squared all over 2C. Yeah. With this, we have come to the end of every possible equation you can come in contact with when you are dealing with capacitors. Application of capacitors. They are used in radio circuits for tuning. Capacitors are used to filter AC harmonics. For ignition system of motor vehicles. To eliminate the sparks when a circuit containing inductance is suddenly open, e.g. in induction coil. These are the practical application of capacitors. Thank you for your time, and next time when we come here, I'm going to use all the knowledge in video 1, video 2, and video 3, which I'm watching right now, to solve all the possible problems that are in this topic. Don't forget to subscribe and share this video. Mind you, I am ruggedly preparing you guys for your WAEC come this year and even the future. My aim is to help you get straight A's in physics. Physics is very, very simple if you can follow all that I'm teaching you in this class. Thank you and God bless you. Bye-bye for now.